Okay, so this video we're going to talk about different types of reactions, including analogy, word, empirical, and ionic. So analogy reactions are usually the first ones that are easier to recognize. They're just word equations used to describe everyday processes. So for example, we could say a frame plus a wheel plus handlebar plus a pedal makes up a bike. And so the left-hand side is reactants, right-hand side is products. We could actually include coefficients in front to describe like one frame, two wheels, two pedals, etc. And then this would be the equivalent of a bike if we use the symbolic form of FW2, HP2. So I have some example problems here. So a CPU plus a monitor plus mouse plus keyboard, what is that going to be? Well, that would be a computer. How about a money plus houses plus board plus dice plus chance cards? Well, that would make Monopoly. Then what makes up a multivitamin? Oh, vitamin A, vitamin B, vitamin C, calcium, magnesium, etc. Next kind of reaction is word reactions. This is the same idea as analogy reaction, but now we're actually using chemical names. So if I have sodium and chlorine together, it's going to make sodium chloride. So notice this side is the bonded side, and so you notice that the chlorine became chloride. So if I have strontium plus iodine, what would that make? Hopefully you realize that would make strontium iodide. So now that ion becomes ide. Okay, and if you're given things with doubles, we're going to switch partners. So just a reminder, you always write the positive guy first and then the negative guy with formulas. So calcium is going to be attracted to the negative acetate and sodium will be attracted to that carbonate. And so this would make calcium acetate plus sodium carbonate. Now the next one is not as obvious what to do for switching partners. We have calcium hydroxide plus hydrochloric acid. So we know the calcium is with this chloric part and hydros with the hydroxide. I think it helps to write the ions. So the calcium ion, hydroxide ion, hydrochloric acid is HCl, so they'd be H plus 1 and Cl minus 1. So now it's easier to see the opposites attracting. And so here you can see you have calcium chloride plus water. Water is the hoe. The next part is an empirical reaction. So empirical reactions is when you write those equations in symbolic form with chemical symbols instead of words. So the key is writing your formulas correctly. So I'd always write your original ions somewhere else on your paper and do the drop and swap. So my first example here is magnesium plus bromine, making magnesium bromide. So here I just translated magnesium to Mg. Bromine is a Br2. It is a Hofrinkel. And then to write magnesium bromide, I go to my original ions of magnesium, bromine, and drop and swap. And we get MgBr2. The next example here is showing calcium phosphate and sodium nitrate, yielding sodium phosphate and calcium nitrate. So again, I would always go back, write your original ions, so you can drop and swap and get these correct formulas. If you do not write the formulas correctly, what happens is ultimately you won't be able to balance the reaction. I also just suggest being familiar with your acids and bases. And so notice on the back of your polyion sheet, you have all those acids and bases listed. Okay, and I have again this reminder, positive ion is always written first, negative one second. Now the next thing is the ionic reactions. Now with ionic reactions, we're not going to worry about balancing these. So what you do is you write that empirical reaction first with your compound labels of solid, liquid, gas, aqueous. And you have to remember that we don't split up solids, liquids, and gases. This is actually listed on the back of your polyatomic ion sheet right above the solubility rules. So we do split up aqueous compounds into their ions, but we have to keep our weak guys together. We only split up ones that are considered strong. When we split our compounds into ions, you do have to keep those charges in the upper right-hand corner. And then what we do is we identify spectator ions. Those are ions that don't really do anything in the reaction, but they appear on both sides in the exact same form. And then our net ionic reaction is what's left behind when we take out those spectators. So the best way to understand this is by looking at an example. So I have this example of sodium sulfate plus barium chloride yields sodium chloride and barium sulfate. So the first thing I do is I'm going to go ahead and figure out my solubility rules. So sodium sulfate, sodium, according to the first solubility rule, sodium compounds are soluble, so that'd be aqueous. Barium chloride is aqueous because of the rule with chlorine, so chlorides are soluble. Sodium chloride is aqueous. And then barium sulfate is a solid. The last rule, sulfates are soluble except for barium. Once you have your labels done, I suggest looking to see if you have any acids or bases, because that impacts if you're able to split up everything or not. I notice I don't have any acids or bases. Just a reminder, acids start with H, and bases have that hydroxide ion. Okay. And so I don't have any of those, so this is a more straightforward example. And I have to remind myself I'm not going to split up solids. Okay, so I'm going to go ahead and split up the formulas into the ions. These are the ions that were used to write the formula. So I have sodium ion plus a sulfate ion, barium ion, chlorine ion, sodium ion, chlorine ion, and my solid barium sulfate. So I only split up my aqueous compounds and make sure that I write my ions correctly. So basically I went backwards from these formulas. So that 2 came from the sulfate, 1 came from the sodium. So if you don't write it as an ion, it's not going to be an ionic reaction. Now your spectator ions are the ions that appear in the same form on both sides. So I notice sodium is the exact same way, chlorine. Okay, so sodium and chlorine. And if you notice, the sulfate and the barium, they're in different forms. That's why that wasn't a spectator ion. Okay, the net ionic reaction is what's left behind when we pull this out. So I have the sulfate ion plus the barium ion yields barium sulfate. So often what this ends up being is the solid, whatever the ions were to make that solid. Okay, let's do one more example. This one's a little bit harder. So here we have H2CO3 plus lithium hydroxide, and we have to figure out our products. Notice this guy is an acid, so it may be helpful to figure out our products by looking at the ions used to write those formulas. So I noticed that lithium is going to bond to the carbonate, and water is bonding to the hydroxide, making a water. Also, just so you know, acids plus bases, they're going to make a salt and water. And once you know that, that does also help when coming up with these reactions. Okay, so then I'm going to use my solubility rules to figure out the labels. Don't forget, acids are aqueous. Lithium, rule number 1, is aqueous. Again, rule number 1, aqueous. And the water is considered a liquid, and we don't split up waters. So I might make a note, don't split. And also, this guy is a weak acid if you look at the list. Weak acids don't split. They need all the help they can get. So for my ionic reaction, I only split up those aqueous compounds that will split up. So I have H2CO3 plus the lithium plus the hydroxide from lithium hydroxide. Then I have the lithium and the carbonate, and the water stays together. So then for my spectator ions, I write the ones that are the same on both sides. This happens to be lithium. So there's that one. And then my net ionic is if I take those spectators out, what am I left with? And that is what I find. So this is like the most complicated type that we probably will see of our net ionic reactions. And this is really telling you chemically what happens. The other thing I want to give you a little tidbit. If I have a strong acid plus a strong base, it will make salt and water. Just a reminder, salts are just a metal with a nonmetal or a metal with a polyion. But its net ionic will always end up being H plus OH minus plus water. It's kind of a nice little tidbit to know that about this. Okay, those are those types of reactions.